Hello, yes, I'm Clara. I'm going to be talking a little bit about mobile chalcophile and fluxes associated with subduction zone magmatism within a continental arc. And I'm mostly just looking at some data that was sort of recently collected that we're thinking about at the moment. So I'm going to give a brief background on chalcophile elements. I know that Nick Barber did a great job with that yesterday, so I'm going to be more brief with it. But chalcophiles, so they're a group that have a strong affinity for sulfur. And they're important in a few different ways. So one of the big things is their economic importance. So they're highly sought after, things like copper, zinc, used in lots of different industries, including in the production of green energy resources. So people sort of want to understand these elements, know where to find them, etc. And they're also incredibly useful from a geochemical perspective, because we can use the different properties of these elements to sort of track different magmatic processes within a volcanic system. But actually, despite the fact that they are very important, generally we're lacking full chalcophile data sets, like the complete set of them, particularly for continental arcs, and a lot of their behaviour is not quite so well known, and sort of based on our understanding in different tectonic settings like oceanic arcs rather than continental arcs, where we sort of tend to find viable deposits of these elements or find them in sort of higher concentrations. And so within this, well, a lot of the studies are also based on whole rock data, rather than looking at melt inclusions, where you're sort of more likely to find a bit more, well, less homogeneous sort of concentrations and more primitive or less degassed compositions. So I'm mostly going to be looking at a group of mobile chalcophile elements. So they're sort of things like thallium, lead, and those are the ones I'm going to be talking about a bit in melt inclusions. So motivation-wise, broadly, so as I mentioned, looking to increase the data set for these sort of elements within melt inclusions for continental arcs, particularly for the less well-studied mobile ones. And also, I'm just going to be looking at, in this presentation, at how the mobile chalcophile element fluxes are affected by the distance from the subduction trench. So that's mostly what I'm going to be covering. So that leads me on to my area of study. So I'm looking at the Trans-Mexican Volcanic Belt. So it's a very nice continental arc in Mexico. And I'm looking at two locations. I'm looking at Colima volcano, which sits in the west, and Popocatépetl, which sits in the east. So they're sort of two very interesting locations, quite ideal in the sense that they're very well characterized, particularly some of the magma chamber characteristics of the units I'm looking at. Which is good because it'll help me sort of understand what the chalcophile elements are doing, given that we know what the processes are. And they share similarities in some magmatic compositions, some activity. So in that respect, they're sort of good for comparison. But they've also got some interesting differences. So one of the immediate visual ones is the distance from the subduction trench. So Colima is sitting a lot closer to the Middle America Trench compared to Popocatépetl. And there's also differences in things like crustal thickness, so it's thicker at Popocatépetl compared to Colima. So these are all things that I sort of want to see what are doing to my chalcophiles. I'm mostly going to be referring to my Popocatépetl as PVC in this presentation, and it's sort of 40,000 years worth of units, tephuras and a few lavas, which are basaltic andesites to dacite in composition. And then for Colima, I'm looking at two main units. So I'm looking at a group 1 unit, which is sort of calc-alkaline basaltic andesites again. But the group 2 unit is the sort of interesting one from Colima because it's a mixed unit. So it's quite a bit higher alkaline compared to our group 1. And so our group 1 unit and some monogenetic silicones are sort of the end members to this group. So it's sort of an interesting one to throw into the mix. In terms of the methodology, so Felix also did a great job of explaining melt inclusions, so I won't go into detail, but I've been looking at pyroxene and olivine-hosted melt inclusions, hopefully to get some more primitive undegassed compositions, less affected by fractional crystallization and so on. Didn't mean to do that. So I got my major element data with an electron microprobe. I also measured sulfur and chlorine data with the probe. And my trace element data and my chalcophile elements were measured with LA-ICP-MS. So it was using the Open University ICP-MS under Fran Jenner. So it's optimized for chalcophile element concentrations, which are so low and hard to measure. The main constraining factor when measuring these was the fact that the inclusions in my units were very, very, very small. So anything smaller than 25 micron had to have a substantially cut down trace element list and basically cut out all the chalcophile elements that I was interested in. So we had to use greater than 25 micron, which was very hard. And so even the biggest ones weren't really big enough to include silver or selenium analyses, which is a bit frustrating because silver and selenium are good for sort of looking at sulfide fractionation and the type of sulfide that you've got in the system. But yeah, that was mostly just because the inclusion was too small to have all the different ablation spots in there. So onto some actual data. So just generally, so I've got my whole rock in the red and blue, and then the green and the orange is the PVC and Colima data. So generally the mountain inclusions are more evolved than the whole rock data. They do show quite a spread of compositions. They've got some more diversity maybe compared to the whole rock. So the podcast petal data are generally more evolved than Colima melt inclusions, so they span from dacites to rhyolites, whereas the Colima is more andesitic basaltic andesite, and you can also see the sort of clear split between the high alkaline group 2 from Colima and the group 1 units, which are lower alkaline. So that's sort of what we expected to see, but there is a bit more diversity, I suppose, in the inclusions compared to the whole rock. So in terms of the undegassed nature of the melt inclusions, they are most likely they've probably degassed sulfur, so that's a shame. But there were some sort of interesting chalcophile trends. So generally the chalcophile elements negatively correlated with magnesium. Copper was sort of interesting though, because there's a very distinct decrease with the whole rock. So again, the whole rock is this one, with decreasing magnesium, but then the minute you get to the sort of melt inclusion area, there's quite a bit more diversity. It's not quite so homogeneous. There's a lot more variability in spread. So we were thinking that that could be something to do with dissolution of sulfides during degassing. So maybe something like that is concentrating copper in the system, but not really concentrating sulfur because the degassing rate is quite high at my volcanoes. But yeah, that's something we're sort of playing with. Right, so this, I've got my melt inclusions normalized to parental morph here. So essentially the peaks are identifying the mobile elements in the system, and I've put in red the ones which are the mobile chalcophile elements which have been identified. So these ones are probably being fluxed from the subducting slab into the mantle wedge, whereas something like copper, for example, down here, it's low sort of enrichment might mean that it's not really being fluxed in from the slab and it's sourced from the mantle wedge. So in general, podcast petal inclusions are more enriched in the chalcophile elements compared to the green Colima data, but there is an exception. So antimony there is actually more enriched in the Colima data. But I'll be mostly focusing on the elements in red in the next few slides. So here we have a graph. So I have a fluid proxy, so barium over niobium, which is sort of a fluid component proxy, I suppose. And then I've got a sediment melt proxy, sort of like sediment melt component proxy on the y-axis. And then I've got red and purple lines, which are basically two end member arcs. So it's a hot end member subduction arc, which is cascades, and isobonin in the purple, which is a cold subduction, mostly just to distinguish between the two fluxes, really, the sediment melt and the fluid melt, fluid flux. So plotting my inclusions on here, so there's quite a distinct trend. So we have the podcast petal data, which sits sort of on the hot subduction line, whereas the Colima, both the group 1 and the group 2, sort of fall in between. So there's probably some different controls and mobility going on here. So when we go back to our map, so we know that Colima is sitting closer to the trench, and we're getting a higher barium for the same sort of thorium. So potentially we're getting more mobilization of barium closer to the trench compared to a podcast petal, where we're probably getting, well, there's a higher sediment melt flux and probably a lot more loss of thorium into the subduction system. So then we took the chalcophile elements and ratioed them with an element which is basically has a similar compatibility to sort of account for fractional crystallization effects. And so we plotted those against the sediment melt flux, and there are two sort of main trends which come out of this. So we have the one on the left, so thallium as the example. There's a very clear correlation between the two sort of units. They kind of lead on from each other, which suggests that thallium is behaving in a similar way to thorium. So in that case, assuming that thorium is being lost further from the trench, we're getting thallium being lost further from the subduction trench, like thorium. And then rubidium antimony also had sort of the same pattern, so these elements have probably got similar controls on their mobility within the systems. And then the trend on the right is a bit different. So there was overlap between the two data sets. So with tungsten as the example, that's probably behaving a bit differently to thorium in the system. And when you look at it with barium, it seems that it's behaving more like barium. So assuming that barium is being mobilized closer to the trench front, we're sort of thinking that tungsten is mobilized closer to the subduction trench as well. And bismuth lead also had similar trends for that. And the difference with all of these graphs is the Kalima group 2 units. So probably something to do with the fact that it's mixing between two end members and two very distinct parental melt. Yeah, but haven't really thought about that one too much yet. So really the summarizing points are, the melt inclusions are decast. We might be getting some dissolution of sulfides during degassing, which is concentrating copper, leading to sort of variability we're seeing in the melt inclusions. And then we've got two sort of different groups of mobile chalcophiles that probably have slightly different controls on their mobility within the two systems. So going on from this, we really have to start breaking this down into individual processes or subduction parameters. So, how is the thickness of the crust, for example, affecting this and the patterns that we're seeing, and also thinking about doing some quantification of the element fluxes also. Yeah, that's it. Thank you.